Good day and welcome to Big Bad Tech. I'm your instructor Jim Pytel, and today we'll discuss rectification and inversion in motor drives. Our objective is to summarize how a generic motor drive rectifies incoming three-phase AC with a fixed magnitude and frequency entirely into DC, then inverts it into outgoing three-phase AC with a variable magnitude and frequency. We'll discuss pulse width modulated inversion and how three properties, fundamental frequency, modulation index, and carrier frequency, respectively influence frequency, magnitude, and quality of the output voltage waveform. This lecture is predicated on the assumption the viewer has watched the Introduction to Motor Drives lecture available at the Big Bad Tech channel. If you haven't watched this lecture yet or only dimly recall its contents, by all means do so now. This in no way is meant to be a complete treatise on rectification and pulse width modulated inversion, but rather serves as an introduction and summary of this complicated topic. Later lectures will expound upon this process and those devices that make it possible in greater detail. This lecture can at most be considered what you need to know before I push you out the door. Expectations having been appropriately bounded, let us continue. Recall we summarized the operation of a motor drive in the above referenced lecture using increasingly detailed configurations of power electronics devices. Let's pick this lecture up at this point and see if we can take it a little further without bottoming out in unnecessary technical details. If we were to picture the motor drive as a magic box, three-phase AC with fixed magnitude and frequency comes in, and three-phase AC with a different magnitude and frequency comes out based on a motor drive settings established by the user. At this level of sophistication, a motor drive is therefore a power electronics device known as an AC to AC converter. Internal to this magic box, this process can be visualized as two other power electronics devices. One, a rectifier, that converts incoming three-phase AC with fixed magnitude and frequency into DC, another an inverter that converts DC into an outgoing three-phase AC with adjustable magnitude and frequency. When viewed at this increased level of detail, a motor drive is a rectifier, an AC to DC converter, followed by an inverter, a DC to AC converter. For this reason, motor drives are somewhat mistakenly referred to as inverters, which actually only describes one half of their purpose. The DC voltage in between the two related power electronic stages is sometimes known as the DC bus or the DC link. The DC bus can store tremendously large values of DC voltage and must be treated with caution. For example, a motor drive operated on 120 volt line to neutral and 208 volt line to line light industrial three-phase AC might have an average DC bus value of over 280 volts. Additionally, energy storage devices like capacitors inside the motor drive can store a lethal charge even after being powered off. For this reason, most motor drives include safety and protection mechanisms that are designed to automatically dump the DC bus within a specified amount of time after being powered off. Take the necessary precautions and follow all manufacturers' recommended lockout and tagout procedures. Test and verify the DC bus in the motor drive is discharged prior to working on or around it. Delving deeper into the inner workings of a motor drive, without bottoming out in an unnecessarily technical discussion, we find several additional functional elements. Both the rectifier and inverter portions include filtration circuits to clean up their respective outputs. The rectifier, as previously discussed, is an AC to DC converter that changes the incoming three-phase AC with a fixed magnitude and frequency into DC. Ordinarily, the rectifier is a type of three-phase AC bridge rectifier that produces an output with an inherent ripple. This ripple is removed with a filtration circuit that produces a relatively stable DC value. As mentioned previously, the part of the filtration circuit may include energy storage devices like capacitors that can store a lethal charge if not properly dissipated. We'll examine diodes, thyristors, natural commutation, and three-phase bridge rectifiers that make rectification possible in later lectures. The other half of the motor drive, the inverter, can also be modeled as having two distinct stages. One being the inverter itself, being the part that changes the incoming DC into three-phase AC with a variable magnitude and frequency, the other being filtration circuit that cleans up this stage's respective output. The inverter, in summary, can be viewed as a collection of high-speed solid-state switches that selectively connect or disconnect the DC link for various amounts of time and with a given polarity. The result being a type of pulsed output. When the filtration circuit smooths out the pulsed output, we are left with something mimicking three-phase AC, only this time frequency and magnitude are variable. This type of inversion process is known as pulse width modulation, sometimes commonly referred to using its abbreviation, PWM. PWM inversion takes some explaining to understand the process in its entirety, but here's a simplified rundown. Let's look at just one phase to make our job easy. You'll have to imagine the other two phases superimposed on top of this one with a 120-degree phase shift. Our goal is to explain how the inverter takes DC voltage from the DC link and makes this complicated unfiltered gobbledygook, which is then filtered into something resembling AC. First, you have to think of PWM in terms of average values for particular sections of a complete AC cycle. For example, if we chopped up an AC waveform with a period of 16.7 milliseconds, a period corresponding to a frequency of 60 Hz, into 24 different sections, each encompassing 15 degrees of a 360-degree cycle, each section could be considered as having a median value representative of that section. For example, the section centered at 0 degrees would have a median value of 0. The section centered at 15 degrees would have a median value of 0.259 of the peak value. The section centered at 30 degrees would have a median value of 0.5 peak value, and the section centered at 45 degrees would have a median value of 0.707 of peak value, and so on. A digitized version of these segmented values would look something like this. You can obviously see the similarity of the resultant AC waveform now. PWM accomplishes this segmented approximation of AC by simply varying the duty cycle and polarity during the specified sections. For example, the section centered on 0 degrees simply has no pulse applied, and the average value is 0. The section centered on 15 degrees has an extremely brief pulse of full voltage applied, such that it appears 25.9% of that section. The section centered on 30 degrees has a longer pulse of voltage applied, such that it appears 50% of that section. The section centered on 45 degrees has an even longer pulse of full voltage applied, such that it appears 70.7% of that section, and so on. When the average value of each section is calculated, take into account the variant duty cycle, the section centered at 0 degrees would have a value of 0. The section centered at 15 degrees would have a value of 0.259 of peak value. The section centered at 30 degrees would have a value of 0.5 of peak value. The section centered at 45 degrees would have a value of 0.707 of peak value, and so on. Accounting for these average values, we are again left with a digitized version of segmented values that looks something similar to AC. The filtration circuit then cleans up this output significantly by smoothing out the step transitions of average value into something resembling AC. Can you dig what is happening here on every level that I do? The unfiltered output of the inverter is, as the name implies, modulated pulses of DC, where the duty cycle is varied to reflect the average values for an individual section. The filter then just smooths it out. A three-phase PWM inverter simply does this 3 times, such that three-phase AC waveforms have a respective phase shift of 120 degrees between each other. We'll examine both single-phase and three-phase AC pulse-width modulated inverters in greater detail in much later lectures on power electronics. But 3 important details I'd like to discuss now are how motor drives vary frequency and magnitude, and additionally influence the quality of the output waveform. Warning, I am taking some serious shortcuts here and making some obvious simplifications I'll come back later to clarify when we examine these circuits in detail. Again, in the interest of expediency, I'm trying to keep this lecture inside the confines of what you need to know and not delve into the nice-to-know realm just yet. First, 2 notable frequencies exist. 1, the fundamental frequency, and 2, the carrier or switching frequency. The fundamental frequency directly influences the output frequency, whereas the switching frequency simply influences the quality or smoothness of the resultant AC waveform. A third quality, sometimes called the modulation index, influences the magnitude of the resultant AC waveform. Let's examine these 3 qualities in turn. First, the fundamental frequency is a measure of the rapidity through which the inverter sweeps through a duty cycle ranging from 0 to 100%, and fundamental frequency directly influences the resultant output of the AC waveform frequency. For our example, the fundamental frequency is set to 60 Hz. It's again best to conceptualize the influence of fundamental frequency using 4 separate sections of the AC waveform: the rising positive, the falling positive, the falling negative, and the rising negative. Given the 60 Hz fundamental frequency, the whole waveform would have a period of 16.7 milliseconds, and each quarter section would be approximately 4.2 milliseconds in length. Given a fundamental frequency of 60 Hz, the inverter varies the duty cycle in a rising sinusoidal fashion from 0 to 100% to generate the rising positive section over 4.2 milliseconds. Then it varies the duty cycle in a falling sinusoidal fashion from 100 back to 0% to generate the falling positive section over the next 4.2 milliseconds. To generate the negative half of the wave, it's the same song, quite literally in reverse, since polarity is changed. The inverter varies the duty cycle in a sinusoidal fashion from 0 to 100% to generate the falling negative section over 4.2 milliseconds. Then it varies the duty cycle in a sinusoidal fashion from 100 back to 0% to generate the rising negative section over the remaining 4.2 milliseconds. In this graph, note I've drawn duty cycles sinusoidally alternating between positive 100% and negative 100%, which if you think about it is kind of nonsense, but it's my way of just reminding you that polarity is swapped for the negative half. Again, the details behind this simplification will make more sense when we examine PWM inverters in depth. Either way, the pulsed output results in average values for a specific section, and then the filtration circuit simply smooths out the pulsed output into something approximating AC. Simply put, given a fundamental frequency of 60 Hz, we experience an output of 60 Hz. The fundamental frequency therefore directly influences the resultant output frequency. By varying fundamental frequency up and down, the inverter can increase or decrease the resultant output frequency. For example, if fundamental frequency was decreased to, let's say, 50 Hz, a frequency corresponding to a period of 20 milliseconds, each quarter section of the waveform would be 5 milliseconds in length. In this case, the inverter varies the duty cycle from 0 to 100% in a sinusoidal fashion to generate the rising positive section over 5 milliseconds. Then it varies the duty cycle from 100% back to 0% in a sinusoidal fashion to generate the falling positive section over the next 5 milliseconds. To generate the negative half of the wave, it's the same song quite literally in reverse since polarity has changed. The inverter varies the duty cycle from 0 to 100% in a sinusoidal fashion to generate the falling negative section over 5 milliseconds. Then it varies the duty cycle from 100 back to 0% in a sinusoidal fashion to generate the rising negative section over the remaining 5 milliseconds. Given the average values of this pulsed output, the filtration circuit then smooths the stepped output into something approximating AC. As can be expected, a fundamental frequency of 50 Hz results in an output frequency of 50 Hz. Coming at this from the other end, if the fundamental frequency is increased to, let's say, 100 Hz, a frequency corresponding to a period of 10 milliseconds, each quarter section of the waveform would be 2.5 milliseconds in length. In this case, the inverter varies the duty cycle in a sinusoidal fashion from 0 to 100% over 2.5 milliseconds to generate the rising positive section. Then it varies the duty cycle in a sinusoidal fashion from 100 to 0% over the next 2.5 milliseconds to generate the falling positive section. To generate the negative half of the wave, it's the same song quite literally in reverse since polarity has changed. The inverter varies the duty cycle in a sinusoidal fashion from 0 to 100% over 2.5 milliseconds to generate the falling negative section. Then it varies the duty cycle in a sinusoidal fashion from 100 back to 0% over the remaining 2.5 milliseconds to generate the rising negative section. Given the average value of the pulsed output per section, the filtration circuit can smooth out this stepped output into something approximating AC. As can be expected, a fundamental frequency of 100 Hz results in an output frequency of 100 Hz. The carrier or switching frequency, in contrast, influences the quality of the output waveform. Switching frequency directly influences the number of sections an individual waveform is divided into when approximating its output. For this example, I've chopped a 60 Hz waveform example into 24 different sections, which produces a reasonable approximation of AC. However, if I was to do this at twice the speed, chopping it into 48 sections, it'd be a far better approximation. If I was to continue doing so at geometrically increasing levels of fineness, we'd be hard-pressed to find any distinction between our switched approximation and a true analog continuously variant waveform. In the interest of expediency, my simplified example is switching duty cycle at 24 times 60, or approximately 1.4 kHz. Switching frequency of motor drives can be 2 kHz up to 16 kHz, with those higher switching frequencies being better approximations of AC, however, coming at the expense of efficiency and necessitating more sophisticated control. These frequencies, by the way, are inside the audible range for most humans below 30. This accounts for the audible whine of VFDs that your ancient dinosaur of an instructor is incapable of hearing. The filtration circuit removes any unwanted electrical noise and voltage spikes. However, it does not do so entirely. Motor drives are notoriously electrically noisy and can sometimes induce unwanted harmonics and voltage spikes if not properly shielded or installed. Moving on, the remaining property, modulation index, influences output magnitude. Simply put, modulation index is a multiplication factor from 0 to 1 applied to the sinusoidally variant duty cycle. A modulation index of 1 for a fundamental frequency of 60 Hz obviously results in a duty cycle sinusoidally alternating between 0 and 100% with a frequency of 60 Hz. The unfiltered output waveform consists of pulses of full voltage where duty cycle for a section influences the average of that particular section. If the modulation index, however, is dialed down a scotch to let's say 0.8, and assuming a fundamental frequency still of 60 Hz, this results in a duty cycle sinusoidally alternating between 0 and only 80% with a frequency of 60 Hz. The unfiltered output waveform still consists of pulses of full voltage, only this time each particular section's average is 80% of what it would be if modulation index was 1. The section centered at 15 degrees would have a median value of 0.207 of peak value. The section centered at 30 degrees would have a median value of 0.40 of peak value. The section centered at 45 degrees would have a median value of 0.566 of peak value, and so on. Given the duty cycle for a particular section still influences the average for that particular section, and the fact that duty cycle has been dialed down to 80%, the output is therefore proportionally reduced to 80% of maximum. If one kept the fundamental frequency at 60 Hz and continued to dial down the modulation index to let's say 0.5, this results in a duty cycle sinusoidally alternating between 0 and only 50%, still with a fundamental frequency of 60 Hz. The unfiltered output waveform still consists of pulses of full voltage, only this time each particular section's average is 50% of what it would be if the modulation index was 1. The section centered at 15 degrees would have a median value of 0.13 of peak value. The section centered at 30 degrees would have a median value of 0.25 of peak value. The section centered at 45 degrees would have a median value of 0.35 of peak value, and so on. As previously, given duty cycle for a particular section still influences the average for that particular section, and the fact that duty cycle has been dialed down to a maximum of 50%, the output is proportionally reduced to 50% of maximum. I know I've shortcut some important details about filtration and the somewhat complicated math and technical details surrounding pulse width modulation, but 3 important comments must be emphasized about fundamental frequency, modulation index, and switching frequency before we put this to bed. First, the observant among you will note that fundamental frequency varies only the frequency of the resultant waveform and not the magnitude nor quality. Second, the observant among you will note that the modulation index varies only magnitude of the resultant waveform and not the frequency nor quality. Finally, the observant among you will note that switching frequency influences the quality and smoothness of the resultant waveform and not the magnitude nor frequency. These 3 important concepts may necessitate some visual aids. Here's an example of the filtered output of one phase of a 3-phase pulse width modulated inverter with a 60 Hz fundamental frequency. a 10 kHz switching frequency, and a modulation index of 1, given a 100 volt DC link. With vertical sensitivity set to 50 volts per division and horizontal sensitivity set to 5 milliseconds per division, we're observing a peak value of 100 volts and a period of roughly 16.7 milliseconds, corresponding to a frequency of 60 Hz as we'd expect. Let's consider this our base state. Here's the filtered output of one phase of a three-phase pulse width modulated inverter when the fundamental frequency has been reduced to 40 Hz and a switching frequency and modulation index respectively remain at 10 kHz and 1. Note by varying the fundamental frequency, magnitude and output quality remain the same, and only resultant frequency is changed, in this case to 40 Hz. Now, here's the filtered output of one phase of a three-phase pulse width modulated inverter when the modulation index has been reduced to 0.6, and fundamental frequency and switching frequency respectively remain at 60 Hz and 10 kHz. Note by varying modulation index, frequency and output quality remain the same, and only resultant magnitude is changed. Finally, here's the filtered output of one phase of a three-phase pulse width modulated inverter when the switching frequency has been reduced to 2 kHz and fundamental frequency and modulation index respectively remain at 60 Hz and 1. Note by decreasing switching frequency, resultant frequency and magnitude remain the same, only resultant quality is changed. One might expect some electrical noise issues given this iteration's wonky output, even after filtration. Alright, that's about it for this brief summary of rectification and pulse width modulated inversion. In conclusion, this lecture took a brief look at how a generic motor drive rectifies incoming three-phase AC with a fixed magnitude and frequency entirely into DC, then inverts it into outgoing three-phase AC with a variable magnitude and frequency. We discussed pulse width modulated inversion and how three properties, fundamental frequency, modulation index, and carrier frequency, respectively influence frequency, magnitude, and quality of the output voltage waveform. Remember to review these concepts as often as you need to really drive it home. Imagine how well lab will go if you know what you're doing. Thank you very much for your attention and interest, and we'll see you again during the next lecture of our series. Remember to tell your Lazy Lab partner about this resource. Be sure to check out the Big Bad Tech channel for additional resources and updates.